Good afternoon.
Good afternoon.
So how's everyone today? Yeah, stunning. All right. All right. So let's see. So today we are going to finish up 7.4, and then I don't know if we'll have time to introduce 7.5 or not. We'll just kind of see how that goes. And then remember on Monday, we're going to, I discovered I don't know if I told you this yesterday, but I discovered what happened on quiz 1, what screwed up, is apparently when I imported the quiz from last semester, is that by trying to do the randomization thing, it didn't import the quiz bank. And so it was randomizing questions from throughout all of Calc 2. So that's totally bizarre to me that it would do that. But, so we throw that one away. So on Monday, we're going to do the 7.1, try again, and 7.3 quizzes. Okay? So Moodle Day, so no classes. I'm not going to broadcast, so it'll be during class time, so you won't have to come in at a different time or whatever. Okay, so that's Monday. So 7.1 and 7.3 quiz. Okay, so any questions or comments or concerns?
Yeah, I forgot that I had to do the 7.2 because of my dentist appointment. So could I do this after this class?
Today?
Yes.
Okay. All right. Okay. So, David, 7.2 quiz. And so we'll get done at 3:40. So we'll say 3:45 to 4:45. Of course, it won't take you that long. But... All right. Anything else?
Mr. Strong, so
Yes.
I tried to watch the video
Yes.
Monday and it wasn't up.
Right.
And so I was gone for EA Tuesday and Wednesday.
Oh yeah, that's right. Yeah,
So I have no idea what I'm doing for half of that. So can I take the 7.2 test Monday during normal time, like third hour, 10 to 11? That way I can actually finish that section.
Oh, I see. Okay. So the 7.2. Okay. So 7.2 Joran Monday at what time?
10 to 11.
10 to 11. Okay, you got it. All right. Let's see. So any other questions, concerns? See, is Joey there in St. John's?
Yeah, he's right here.
Okay. All right. I thought I saw him come by, but I don't know. I thought maybe it was my imagination. Okay. Well, let's go to our notes. So we are on 7.4 and we're on part 3. Let's see here. All right. So for those of you guys that weren't here yesterday, we ended up having less than half of the people. So we only went like half the time. So That's why we didn't get very far. Okay, so part 3. So now we're kind of switching gears in this lesson. It's actually, this used to be 2 small sections, and so it's kind of fine. I kind of like it better as 2 sections anyway. But so here we're going to talk about the exponential growth and decay that when we introduced the lesson on Tuesday, I guess. So we use the exponential growth model. Dy dt equals k times t. So the derivative is k times t, where k is a constant, with the solution of this differential equation, y equals y sub 0 e to the kt. Now, so we get this formula from differential equation, from separating the separable differential equation. That's why they put them together. But this formula that we use, we actually used it in pre-calculus, in college algebra. And so as we get to the problems, the word problems, they're really, it's not going to even feel like it's calculus. It's going to feel more like trig problems. They're usually in the section that in chapter 5 in the book that we use that involves the exponential and logarithmic functions. So it's going to feel more like pre-calculus, the rest of this section, than calculus, because the calculus is already involved in getting that equation. Okay. All right. So let me just read the problems here. Let's see. Wait. Okay. All right. So actually, if you look at on your student success organizer, practice 3. This is kind of what we're focusing on. So it says the biomass of a yeast culture is initially 29 grams. So then the initial amount, that's our y sub 0. And so then that's 29 grams. All right, so that's what that means, the initial amount. All right, then it says after 30 minutes, the mass is 37 grams. So then the time in this problem is measured in minutes, okay? And so the y of 30 is 37 grams. So in other words, when t equals 30, y is 37. Okay? So that's kind of what that is saying. So then it wants to know how long does it take for the number of yeast culture, the amount to triple or double or whatever. Okay? Now, let's do the doubling one first, and then I'll have you do the tripling one. Okay? So how long it takes to double, well, when you plug in the initial information, then you get 37 equals 29 e to the kt. Now, you might think, okay, we're trying to find how long, we're trying to solve for t. But in all these problems, they kind of have the same format, and that is that first you find k, the rate of change, then you find whatever it is that's asking you to find. So we're going to first find k. All right, so to find k, first thing we do algebraically is divide each side by 29. All right, then we're going to rewrite it as a natural log. So that would be log base e, so ln of 37/29 is equal to 30k. So remember what the log is equal to is the exponent. And then to solve that for k, divide each side by 30. And so then this, when you put it in your calculator, that's going to be your k. All right. So let's just do that. So get out your calculator. Let's just make sure that you don't have any problem keying that in. All right. So just put in the natural log of 37/29. I'll divide it by 30. And then usually for k, because it's an exponent, we usually carry it out to at least 4 decimal places. So instead of the normal 3, we carry it out to 4 because it's an exponent. Okay, so let's just make sure you don't have any calculator issues putting in this value for k. Okay, any problems there? All right, so now, so with that k, now I can answer the question. Is that at that growth rate, how long is it going to take to double? So to double means if it starts at 29, you're going to end up at 58, twice as much. And so, so 29e to the kt. And so then when I divide both sides by 29, I get 2 equals e to the kt. And so then now I'm solving for t, but I still am going to rewrite it as a log. So that's log base e. So the natural log of 2 equals 0.0081t. And divide by 0.0081. And so it's going to take, at that growth rate, more than 85 minutes to double in mass. All right, so what I want you to do is just kind of tweak that a little bit and figure out how long it takes to triple in mass. All right, so Chloe, do you have this one?
135.63 minutes.
There you go. So you might say, well, why isn't it exact? Well, it depends on, like, if you put in the 0.0081, or if that was the calculation you used in your calculator. You know how, like, if you use like the last answer feature so that you don't have to retype it, then it's actually more exact. So, but that's we're close enough to the same answer that I know we're good. All right. Any questions on that one? All right. So good job. So, okay, so let's go to the next part. All right, curing a disease. So the number of people cured is, now, does anyone know what the alpha symbol means mathematically? If you use it in a mathematical context. Anybody know what it means?
Doesn't it mean directly proportional to?
It does. It does. Directly proportional. Very good. So the number of people cured is directly proportional to the number infected. Okay? So usually, like if you're curing 10% or whatever, it kind of works like that. So here in example 4, all right, sorry. Okay, so here we have an initial number of infected people is 10,000 for disease. All right, so again, we're using the same formula. So it's kind of weird. Well, anyway. So let's say that after 1 year, 20% are cured. Okay. So that means that, so then you put in 1 for T. So now T is in years. And then, so where did the 8,000 come from? Well, if 20% were cured, then we've gone from 10,000 people infected to 8,000 people infected. So it's the number of infected that you put there. So now you solve for K. All right, so the first thing you do, divide each side by the coefficient, 10,000, and then rewrite it as a natural log. Now this one I did a little differently, just mathematically, algebraically, just to show that some people, instead of rewriting it as a log, they'll take the log of both sides. And that works too. Because the natural log of e to the k is just k. So the natural log of 0.8. So that's what our k is. Now I'm going to leave it like that so that I can get a more precise answer. Okay? So now the question is, how many... So at what point, how long will it take for the disease to be 90% eradicated? Okay, 90% eradicated. So that means we've gone from 10,000 to 1,000 people infected. So we do 1,000 equals 10,000 times KT. So the K is natural log of 0.8. And so then when I solve that, divide each side by 10,000. E to the natural log of 0.8t. So the E and the ln will cancel, bringing down the 0.8. And now you rewrite that as a natural log, or as a log. So that's log of 0.8 of 0.1 equals t. And so now you put that in your calculator, and you get 10.318 years. Okay? So that disease will be, there'll only be 10% of the number infected. Okay? All right, so now do practice 4, where it says that suppose that in a given year, so in 1 year, the number of cases is reduced by 20%. So your K is going to be, let's see, did we do 20% on this one? Yeah, so the K is going to be the same. If there are 10,000 cases today, how many years will it take to reduce the number of cases to 500? All right, so Aiden, what do you have? Or when you get it, tell us what you have.
I got 13.4251 years.
that's it. Good job. Any questions on that?
Can you just leave that on the board for 1 second, please?
Sure.
Thank
And if
you.
you need me to go through it, just let me know. So I don't know if you've been following the coronavirus, but there's actually the number one internet search yesterday was, does Corona beer cause the coronavirus? You believe that? That was the number one search. Even in China. So anyway. But what they're worried about is if that virus breaks quarantine and starts growing exponentially, you know, that's when you have a pandemic, a worldwide epidemic. So, okay. All right. So what you have to, when you're doing these problems, you have to understand that it seems like as kids, we're programmed to think linearly. It's like, okay, if you work 1 hour, I'll give you $5. So if you work 4 hours, you get $20 or whatever. And that's very linear. All right. And so, but there's also, that's what's called an arithmetic progression. Okay. Then there's geometric, where you multiply by the same number each time. But then exponential, what we're talking about, is even once it kind of starts slow, but once it picks up, the graph is very steep because the variable, the time element, is in the exponent, and so it grows just crazy. All right. So the next example is radioactivity. All right, it says if y sub 0 is the number of radioactive nuclei present at time 0, the number still present at any later time t would be, okay, we're using the same formula, only slightly different. What we're doing here to emphasize the radioactive decay is we put a negative in the formula. Now, you don't actually have to do that. It's just that if you don't, then the k is negative because time's not negative. All right, and then the formula for half-life, that's the next blank. This is the formula for half-life. It's y equals y sub 0 times 1/2 to the t divided by h, where t is time and h is the known half-life. Okay. So can anyone tell me or explain what is half-life?
It's like when you have like a sample of like a radioactive substance, and a half-life is how long it takes for half of that sample to be radioactive. So
Excellent. Thank you so much for not using the word zombie in your explanation, because usually I get somebody saying, "Oh, half-life, that's when you're a zombie." No, you're not. It doesn't have anything to do with zombies. All right. Okay, so it's the amount when you have half of the radioactive substance left. Okay. So this is actually how that formula is. We come up with that, and so y sub 0 equals 1/2 to the th. Okay. If you don't know the half-life, but you know the k, you probably want to write this down too, next to that half-life formula you just wrote down. T equals the natural log of 2 divided by k. That's how you compute half-life. Actually, I'm going to And so in the last formula, we actually use H. So I'm going to say H equals the natural log of 2 divided by K. That's how you compute the half-life of a substance if you know its rate of decay. All right, so okay. So this says the half-life of polonium-210. All right. So if we're told that polonium-210 has this many atoms after so many days, when the number in front of the T, when you're given something like this, that is the K. That's the rate of decay. So remember, it's negative KT. So if you're given this, then the K would be 5 times 10 to the minus 3. Okay? So that is the rate of decay. So then to find the half-life in days, so the time, or I guess H, it doesn't matter which variable you use here. So it'd be the natural log of 2 divided by the given rate of decay. So in this case, natural log of 2 divided by 5 times 10 to the minus 3. And so you can just put that in your calculator like that, or you could use the elevator rule or whatever, and you get 138.629 days. Okay, so on practice 5A, it's kind of weird how it's written because the font that I was using wouldn't let me do an exponent on an exponent. Like I can write it. So like here when I have an exponent on this exponent, it didn't like that. So when I write this, so so I was able to do it on Smartboard, but it's on your paper, it looks a little bit weird. So, but this is the K, is going to be 4 times 10 to the minus 3. All right, so see if you can figure that out. All right, so Hannah.
Do you want T or do you want the final answer?
I just want the T.
Okay, then I have that. I have 173.287 days.
Okay. So there you go. Okay, so it's just the natural log of 2 divided by this K. So that's the half-life. So if you start off with 10 grams, then what that means is after 173.287 days, you're only going to have 5 grams. And so the rest of it, it's emitting energy. And so as it emits energy, it's losing mass. And so that's kind of the rate at which it's losing the energy. Okay, so one way that that radioactive decay is used a lot is in carbon dating. So scientists who use carbon dating use a figure of 5,730 years for its half-life. So what I mean by carbon dating. So this is the idea behind carbon dating, is that we're all carbon-based life forms. We all have carbon in it. And so every organic thing on the planet Earth, every more organic being has carbon. All right. So, and we all have trace amounts of radioactive carbon. So carbon-14 that we have is radioactive. Carbon-12, regular carbon, that most of what the carbon that we have is not radioactive. Okay. So what happens is that this ratio is the same in all of us. But then what happens is when we die, then we don't absorb any more carbon. And so the radioactive carbon is emitting energy, and so its mass is going down. And so the ratio of radioactive carbon to regular carbon is changing. And so what they do is that they measure. Now, here I have an example of 1 part per 10 or 4 parts per 40 or whatever. It's really not that. It's like 1 part per million or billion. I mean, it's very trace amounts. But the longer we're dead, the smaller that ratio becomes. And so then what they can do is look at what that ratio of radioactive carbon to regular carbon is, and then they can determine how long it's been since you died. Okay? And so that's what they call radioactive carbon dating. Okay? Now, I'll just tell you right now, I have several issues with this method. I personally think it's not extremely scientific in that it has a lot of assumptions that I don't think is true. One of them is that it assumes that the ratio of radioactive to regular carbon in the atmosphere is always the same. And see, we know that's not true with volcanic eruptions. If there was an asteroid that hit the Gulf of Mexico, if there was a worldwide flood, all of those things would drastically affect the ratio of radioactive to carbon. But what it does do is you can say that this thing is older than this. But I just don't, when I see something that says, oh, this thing is 345 million years old, I think that's a bunch of crap, personally. And I've argued science teachers about that, and they always have to concede that I'm right, but they're like, well, it's the best we've got. And I'm like, well, I just, anyway. You can, so talk to your science teacher about it, see if they have another viewpoint. But anyway. Okay, so so it says, find the age of a sample in which 5% of the radioactive nuclei originally present have decayed. So we use this same formula. Okay, so let's say that 10% is decayed. So I'll do 10% and then you do 5%. So in 10%, then you might say, well, I don't know how much we have to start with. Well, it doesn't matter. Because what's going to happen is, like, if we've lost 10%, then we have 90% of y sub 0. And the first thing, when you divide by y sub 0, it goes away anyway. Okay? So it doesn't matter how much you started with. So here you've lost 10%, so you have 90% left. And so then what we're going to do is use the K that's for carbon-14. So this is always the same for every carbon problem, every carbon dating problem. K is the natural log of 2 divided by 5,730. Although, see, this is the other thing that irritates me, is every few years they actually will come up with a different number for this. I'm like, come on, how accurate can that be if they're revising that number every 10 years? Do they go back in all these museums and, change the date on this dinosaur bone? No. So anyway, That's just me, okay? All right, so then you plug that in for K, and then you solve for T. So I actually solve for T, leaving K in there, and then I just plug in the K at the very end, and then I get the final answer, and so this would be 870.977 years, okay? So that's how long it would take to lose 10% of its mass for this object. Okay, so of the carbon. Okay, so find the age of a sample in which 5% of the radioactive nuclei originally present have decayed. So this was 10, 10% is decayed, so we have 90%. So now you're going to just figure out what if only 5% is decayed. How old is this sample? All right, so Hannah, it's your lucky day. I was thinking we start off with 3 Hannahs, and it's like survival of the fittest. So anyway, when you've got it, let me know.
Yeah, I got 424.023 years.
Okay. So again, approximately 424 years. So everybody good on that? So the other thing is since it's like the ratio is so small. Like I said, it's like 1 part per, I can't remember if it's million or trillion or something like that, that the human error in measuring it to begin with is just astronomical. It's like if you miscount one molecule, one atom of carbon-14, it throws off your calculations. So anyway, I'm going to quit talking about it because you guys are thinking I'm crazy. Okay, so the last part of this is also important. This is called Newton's law of cooling. And well, here, this is kind of how we get it. Let me go ahead and just give you the notes. Okay, so this is the formula that you write down. So H is the temperature of the object, and H sub S is the surrounding temperature. I'm not sure why this book uses H's instead of T's. Most books use T's. H sub 0 is the initial temperature. All right, and then you have times e to the negative kt again. So what this does is it tells you, like let's say you take a casserole out of the oven and you're wanting it to cool down before you serve it to your family. And if you, well, let's back up. Let's say that you're working at a fancy restaurant. You take something out of the oven, and the chef says, we want to serve this when it's exactly 72 degrees. And so they will actually figure out how long this should be out of the oven. So we don't want to burn our customers' mouths so there's lawsuits, but at the same time, we want it perfect. And so that's an application. Or like, I don't know if any of you have ever tried to cook meat that's frozen. Have any of you ever tried that? Well, it's a bad deal. Okay? If you try to cook like a steak that's frozen, you'll ruin it. So you have to thaw it out. Or like if you try to like take your Thanksgiving turkey out of the freezer and throw it directly in the oven, you just ruined your turkey. So it has to thaw first. Okay? Have you tried that, Chloe? Have you tried to cook frozen meat? Or
Yeah, I have.
okay, was it a disaster?
I learned my lesson. Yep.
Right. So what they do in again, like in places that in restaurants, that they will actually figure out how long it takes to. I mean, they'll know from experience or whatever. But we can actually figure out exactly how long it takes for the meat to thaw or to be at whatever temperature we want it to be. Okay. Now, so any kind of change in temperature. Now, let me just do one other example here. But like, have you any of you like watching like murder mysteries or anything, detective shows like CSI or Hawaii Five-O? Any of those? Does anybody of you guys watch those? A little bit. Okay. Have you ever watched those? When the detective comes on the scene, he always asks the coroner, what's the time of death? Because that's important in investigative procedure. And they'll say, well, he died right around, 10 to 12 p.m. Now, have you ever wondered how they do that? Does anybody know?
How much the body is cooled.
Okay. So, yeah, so what it is it's like they're using Newton's law of cooling. And so it's actually the liver temperature. They actually measure the temperature of the liver and they see how much it's changed. And then based on how much it's cooled, they can calculate the time, because as soon as a person dies, then their body starts cooling because the blood isn't pumping anymore. And so as the body is cooling, they can say, oh, it's been cooling for 3 hours. So therefore, the time of death is blah, blah, blah. Okay? So, using Newton's law of cooling. All right, so let's jump to, practice 6. So suppose that a cup of ramen noodles. So I'm not going to have you, work with a dead corpse or anything, a corpse. We'll work with ramen noodles. So suppose that a cup of ramen noodles cooled from 85 degrees Celsius to 55 degrees Celsius after 10 minutes in a room whose temperature was 20 degrees Celsius. Okay, so we stop right there and find K. All right? So remember, you got to find K first before you can then answer the question. So see if you can plug into the formula all these numbers and calculate K. All right, Joey, when you've got K. Or if you get stuck, let me know.
For K, I got negative 0.0619.
Okay, so 0.0619. So if you put the K with the negative with the K, it doesn't matter. What I'm saying is you can have the negative separate from the K, which it would be positive, or like you did, put the negative with the K, that's okay. Okay, so that's K. All right, so now we are going, it says how much longer will it take the noodles to cool to 30 degrees? Now, you can either have the initial temperature be 55, or you could keep it at 85 and just know that you've already used up 10 minutes. And so adjust your answer that way. Okay? So again, you can start with your initial temperature, either one. Okay? So it might be easier to just start it at 55 because it's gone from 85 to 55, and now you want to know how long is it going to take to go from 55 to 30. All right? So see if you can do that. All right, so Chloe, do you have it?
I just set it up, but I didn't solve it. I'm not
Okay.
sure if everything's in the right spot.
Okay. So is that the setup?
Yeah.
Okay. So you would subtract, divide, natural log. Okay, does anybody have the final answer yet? All right, go ahead, Joey.
Okay, I got 5.436 minutes.
Whoop. So let's see here. Okay. So I got 20. So here when you subtract, you get 10.
Yeah,
and
I
here
think
35. What?
I did put the wrong numbers in on the left side, but the right numbers in on the right side.
Oh, okay, okay. So go ahead and write this down, and then if then check your work, and then if you don't get it, let me know, and we'll go over it on Tuesday. So remember, no broadcast on Monday. We're doing a Moodle quiz for 7-1 and 7-3, and then we'll kind of go from there. All right. So you guys have a great weekend, and we'll